All right, in this lesson, we are working with radicals. And so we're going to start with simplifying, and then we are going to get into some operations and then some formulas that involve radicals. And so starting with simplifying, you want to recognize your perfect squares. And so we have them listed here. And so when you see square root of a perfect square, it's just a integer. So square root of 100 is just 10. That's simplified. If you see square root of a number that is not a perfect square, your goal is to get all of the perfect square factors out from under the radical. And so a property of square root and radicals is that if you have a product under the radical, you can break it up into its individual radicals. And so 12 can be written as a product of 4 times 3. The reason why I chose 4 and 3 instead of like 2 and 6 is because 4 is a perfect square factor. And so now when I break up this product into their individual radicals, I know the square root of 4 is 2 and 3 is not a perfect square. So it would stay under the square root, and that would be my final simplified answer. 3 has no perfect square factors, and so I know I'm done. Okay, looking at 72, an immediate perfect square factor that comes to mind for 72 is 9, because 9 times 8 is 72. And so I can break that up into square root of 9 times square root of 8, and square root of 9 is just 3. Now I'm not quite done, because 8 still has a perfect square factor, because 8 is 4 times 2. And so I can break the 4 and the 2 up. And square root of 4 is just 2 with no square root. And then that other 2 under the radical has to stay. And so I have a 3 and a 2 outside getting multiplied, so that is 6. And then that square root of 2 just stays. They're all just being multiplied. Okay. And so looking at number 4, we're going to ignore the 5 outside for right now and just focus on the 40, because that's what's under the radical. A perfect square factor of 40 that immediately comes to mind, I'm going to write that off to the side, is 4 times 10, which would then be square root of 4 times square root of 10. Square root of 4 is just 2. Now, thinking of factors that multiply to 10, 1 and 10, 2 and 5, none of those are perfect squares, and so we're done at this point. And so square root of 40 is the same thing as 2 square roots of 10, and so the 5 and the 2 outside would then get multiplied to be a 10, and 10 square root of 10 would be our final answer. Okay, so every time you commit to a final answer, just double check and make sure the number under the square root is not a perfect square and does not have any perfect square factors like I did over here. Okay, looking at 48, I know 48 breaks into 4 times 12. And something that's also helpful is to kind of just make a factor tree of all the prime factors, and then you can look for perfect squares that way. So 4 is 2 and 2. We know that's a perfect square. But 12 is 4 and 3. And then 4 breaks apart into 2 and 2. And so when you go down to all the primes, you kind of just collect pairs. So here's my primes. And then so make your radical, and anytime you see a pair, that means it was a perfect square factor. And so I have a pair of 2s. I can write a 2 outside. And then I have another pair of 2s. So another 2 would be outside the radical. Kind of think of it like matching socks. Once you find a pair, fold it into one and then write it outside the basket. Put it outside the basket. And if there's more than one, you're going to multiply. Okay, and then we have this lonely 3 that doesn't have a match, which means he was not a perfect square factor, so he stays inside. And so this simplifies to 4 square roots of 3. Okay, and so 4 square roots of 3, and then we still have that 2, and so that becomes 8 square roots of 3 for my final answer. Okay, looking at that square root of 8. Square root of 8 is the same as 4 times 2, which is square root of 4 times square root of 2, which is 2 square roots of 2. 5 and 2 get multiplied to be 10, so we have 10 square roots of 2 for our final answer. Okay, for this next set of examples, we are doing operations. We can add and subtract. And so when you add and subtract, you can only combine like terms. And so it says combine like radicals. Okay, and so they have to have the same number under the radical. That number under the radical actually has a special name called the radicand. Radicand. So you might hear me say that. Okay, so here I see we have square root of 3 and square root of 3. So think of that as 7x plus 5x. You know that would give you 12x. And so that would give me 12 square roots of 3 for my final answer. Okay, here I have 7 square roots of 3 minus 5 square roots of 3. So that is 2 square roots of 3. Here I have 8 square roots of 3 minus 1 square root of 3. Picturing that as 8x minus x, that would be 7x. And so this would give me 7 square roots of 3. Okay, for this next one, these are not like radicals, okay? One of them is a square root of 2 and one of them is a square root of 8. And so one thing we need to do first is make sure they're all simplified. 8 is the same thing as 4 times 2. So that means this radical can be simplified because it has a perfect square factor. And so square root of 4 times square root of 2 then gives me 2 square roots of 2. Okay, and so I can rewrite this as 7 square roots of 2 minus 5 times 2 square roots of 2, which we know is 10. We have this 5 times this 2 to get 10. Okay, so now we have 7 square root of 2 minus 10 square root of 2. You can think of that as 7x minus 10x, which would give you negative 3x. And so that's negative, not negative 3. Yes, negative 3. Negative 3 square roots of 2. Okay, in number 5, one of these is a square root of 2, and the other is a square root of 3. And so these are not like radicands, and neither of them can be simplified. Neither 2 nor 3 has a perfect square factor. And so these are not like radicals. Not like radicals. Cannot be simplified. Okay, on this next one, we have a square root of 3, a square root of 5, and a square root of 27. And so we can't combine the 3 and the 5, and definitely not the 27, but the 27 can be simplified. So looking at this 27, I know that is 9 times 3, which means a 3 could come outside the radical. The 4 and the 3 get multiplied to give me 12 square roots of 3. Okay, copying down the rest of the problem. I had 7 square roots of 3 minus 2 square roots of 5 plus 12 square roots of 3. Now we have some like terms. 7 square roots of 3 plus 12 square roots of 3 is 19 square roots of 3. And then that square root of 5 has to stay because it cannot be combined. And so my final answer would be 19 square roots of 3 minus 2 square roots of 5. All right, on this next set of examples, we are multiplying radicals. And so that property we talked about earlier can go in reverse. If we are multiplying individual radicals, we just multiply their radicands, their individual. Okay, so here I've got square root of 3 times square root of 2. So we just multiply the 3 and 2 under one radical to get square root of 6. Okay, on this next one, we are multiplying, and you can even add a multiplication dot right here, 7 times square root of 3 times square root of 2. And so we can combine these radicals to be square root of 6. And we still have the 7 outside. Okay, here we have a set of parentheses, but the parentheses aren't serving any kind of purpose. We can add multiplication dots. We can separate these out. So I like to put the numbers that do not have a radical in front and then put the radicals at the end. You're allowed to rearrange terms in a multiplication strand, which I think is helpful. Okay, and so 8 times 2, those can become 16. And then the square root of 3 times square root of 5 is square root of 15. If it doesn't have a radical, it stays outside the radical. If it does have a radical, it gets combined with other radicans. Okay, and then before you commit to your final answer, make sure that you can't simplify what's under the radical. So the 15, of course, is just 3 and 5 as the factors, and so that has no perfect square factors. And so this is our final answer, 16 square roots of 15. Okay, here we would multiply the 6 times the 4 and get 24 square roots of 2. Again, these parentheses don't really have a purpose. You don't like distribute the 6 under the radical. Everything is just being multiplied by every term. Okay, here, again, let's just rearrange some terms. Let's put the 5 in front, and then the 2, square root of 2, and then the square root of 6. Remember, these are all just being multiplied, and so we can combine the 2 and the 6 under the radical to become 12. Okay, and I just highlighted that, but that's actually not our final answer. We can simplify this 12. 12 is the same thing as 4 times 3, which is a perfect square factor, which means we have square root of 4 times square root of 3, which is 2 square roots of 3. Bring back the 5, and so my final answer would be 10 square roots of 3. Okay, looking at this next example, I have a 2, a negative 2, and a 4 all being multiplied by each other. So I'm going to go ahead and just put those front because I'm going to combine those. And then I have a square root of 3, a square root of 5, and a square root of 10. Okay, and so 2 times negative 2 is negative 4, times 4 is negative 16 for that number out front. And then 3 times 5 times 10 is 150. Okay, 150 can be simplified, and so if you want to go with the factor tree, we know that 150 is 15 times 10. We know 15 is 3 times 5, and 10 is 2 times 5. These are all my prime factors, so I'm going to circle them, and we're looking for pairs. I see a pair of 5s, and so that means I can write 1 5 outside the radical. And then we have a 3 that doesn't have a match, so it goes back inside. And we have a 2 that doesn't have a match, so it goes back inside. Okay, and so we can combine the 3 and the 2 to become 6. And so that leaves us with 5 square roots of 6. So this 5 would get multiplied by this negative 16 out front. And then negative 16 times 5 is negative 80. So negative 80 square roots of 6 would be our final answer. Okay, in this next section, we are dividing radicals. And so when you divide radicals, it's the same idea as multiplying. If you have square root divided by square root, you can combine them under one square root. Okay, and so looking at number 1, we have a 7 and a 14 outside the radical, so we would just simplify that as we usually would. 7 over 14 is 1 over 2. And so 1 square roots of 3 over 2, and usually we don't write the 1. We would just write square root of 3 over 2. Okay, here we have a square root of 6 over a square root of 2. And so you can combine that under one radical, leaving the 7 outside. And then we know 6 divided by 2 is 3. It's important to notice that numbers outside the radicals don't interact with numbers inside the radicals. And so because 6 and 2 are both inside a radical, we can put them together. So that leaves me with square root of 3. Okay, here we have 12 divided by 4 under the radical, which is just 3. Here, let's focus on the 8 over 16 first. 8 over 16 is 1 over 2. And then we have a 15 over 3 inside the radical, which simplifies to 5. So there's two ways you could write this. 1/2 square root of 5, or since that 2 is on bottom, you may just see it as square root of 5 over 2. Okay, looking at 6 over 14, both of those are divisible by 2. And so when I divide both of those by 2, I get 3 over 7. And then square root of 12 over square root of 3 can simplify to square root of 4, which is just 2. Okay, and so I have a 3/7 times a 2. Multiplying those, you could treat that as 2 over 1. 3 times 2 is 6. 7 times 1 is 7. So this whole expression simplifies to 6/7. Okay, in this next one, I have 15 over 40. And then I have a square root of 24 over 3. 15 over 40, we can divide both of those by 5 to get 3 over 8. And then 24 over 3 simplifies to 8. This 8 has a perfect square factor. And so that is the same thing as 4 times 2. Which is square root of 4 times square root of 2, which is 2 square roots of 2. So now I have a 3/8 times a 2 times a square root of 2. Okay, and then when I multiply these numbers outside, I get 6 over 8 square roots of 2, which both of those are divisible by 2. And so that gives me 3/4 square root of 2. And then again, you can write both of those terms over the 4, but it's very, very important. I'm gonna go ahead and highlight this. Do not simplify the 2 over the 4. That is a very common mistake. 2 has a radical, 4 does not. They cannot interact and simplify. Okay, this next set of examples, we are doing something called rationalizing the denominator, meaning we don't want any square roots in the denominator. So for this first example, I have a square root of 2. And so the trick is you just multiply the denominator by itself. Okay, whatever you do to the denominator, you have to do to the numerator. You can't just change the bottom. And so you multiply both the top and bottom by square root of 2. Just like we can divide top and bottom of a fraction to simplify it, you can also scale top and bottom. Okay, and so now that gives me 7 square roots of 2 on top, and square root of 2 times square root of 2 is square root of 4, which we know is just 2. And so that's why we are multiplying the square root by itself, because that creates a perfect square factor, 2 times 2, which then simplifies to 2. Okay, this can't be simplified. The square root of 2 cannot interact with the 2 on bottom, and so that's our final answer. Okay, here we are going to multiply top and bottom by the square root of 3. Top and bottom, can't emphasize that enough, which leaves me 12 square roots of 3 on top, and then the square root of 9 on bottom. 12 square roots of 3 on top, square root of 9 is just 3. And then now this 12 and this 3 are both outside the radical, and so we can simplify 12 over 3 to 4. Okay, looking at number 9, multiply top and bottom by square root of 2. So on top, I get 6, and then square root of 3 times square root of 2 can combine under one radical. And then we get square root of 4 on bottom. That gives me 6 square roots of 6 on top, and then just a 2 on bottom. And now my two numbers outside the radical, 6 and 2, can simplify to 3 square roots of 6. 6 does not have any perfect square factors, and so we are done. All right, this last section of notes, we are using two formulas that involve a square root. The more familiar one is the quadratic formula because we use that in Algebra 1. And the less familiar one that you will see in geometry is called the distance formula. All right, so this distance formula calculates the distance between 2 points. And so when you are asked to find the distance between 2 points, label your points x1, y1, x2, y2. So it says find the distance between these points. So this will be my x1, y1, x2, y2. Okay, and so in my formula, I have x2 minus x1. So I'm going to have 1 minus 9 squared from that square. And then I have y2, or a plus sign. And then I have y2 minus y1. y2 minus y1, which is negative 4 squared. Okay, now that I've plugged those in, let's do some simplifying. So I have 1 minus 9 inside those first parentheses, which is negative 8. And then negative 2 minus negative is the same thing as negative 2 plus. Minus negative is the same as plus. So negative 2 plus 4 would just give me a positive 2. Negative 8 squared is positive 64. Anytime you square a negative, it becomes positive. And then 2 squared is 4. Okay, and then 64 plus 4 is 68. Okay, and so now we just need to simplify the 68 if we can. And so let's come over here and make a factor tree and look for matches. Okay, 68 is even, so I'm going to use 2 and 34, 2 and 17. 17 is prime. Okay, and so 2, 2, and 17 are my primes. The 2 pairs up, meaning I can write a 2 outside. And then we're left with a 17 under the radical. Okay, and so my final answer would be 2 square roots of 17. Okay, the next formula that involves square root is our quadratic formula. And so when you have a quadratic equation that you're trying to find the solutions to, you can use the quadratic formula. And so here we need to identify our A, our B, and our C. And so A is 3, B is 4, and C is negative 2. Okay, and so just looking at where these go in the formula, C only goes in one place. B goes in 2 places, negative B, and then we have a B squared. And then A goes in 2 places, A and A. Okay, and so let's plug those in. X equals negative B plus or minus the square root of B squared, minus 4AC all over 2A. Okay, and so B goes in 2 places, and then A goes in 2 places, and C goes in 1 place. And so that leaves me with a negative 4 plus or minus 4 squared is 16. And then looking at this expression here, we have negative 4 times 3, which is negative 12. And then negative 12 times negative 2 is positive 24. And then 2 times 3 is 6. Okay, so the radicand, 16 plus 24, gives us 40. And now we just have to try to simplify this square root of 40. So off to the side, we know that is 4 times 10. 10 is 2 times 5. 4 is 2 times 2. Here's all my primes. We have a pair of 2's. And then we have a lonely 2 and a lonely 5. So the 2 and the 5 end up getting written right back inside. The 2 that pairs up gets written outside. And so that simplifies to 2 square roots of 10. So coming back over here, I've got that negative 4. I've still got the 6, but now I have plus or minus 2 square roots of 10. Okay, and so remember, only numbers outside the radical can interact with each other. So looking at the negative 4, the 2, and the 6, all of those can be divided by 2. And so think of dividing each of them individually by 2, which would then give me negative 2 plus or minus 1 square root of 10 all over 3. And we just leave that 1 invisible. And so that would be our final answer.